All right, welcome back. Homework announcement, not due until Thursday, obviously. The new homework, problem set 6, is now available. Test is 1 week from Thursday, and I'm looking for a place to have a review session for the test. What we're going to go over is basically problem set 5. Problem set 5 concerns the one that's due Thursday, yeah.
When is problem
We'll
set
pretty
6?
much outline everything that you need. Excuse me?
When is problem set 6 due?
Problem set 6 is due on Tuesday. As in 10 hours from now. Dun dun dun. No. As I said 30 seconds ago, yes, the tutorial will be on Friday. So, most of what's on problem set 6 is just me being mean, harder problems of the same material that we've covered. On Thursday, we'll kind of do a review on that problem set as well. Problem set 5. No, everybody's grumbling. Magnetic induction. There is, what's the best example? Magnetic induction, you've got a generator, something that spins. Well, what's in a generator? A whole bunch of magnets. What happens? You get current coming out of it. And the thing that we look at is this right here. EMF is negative d5b dt. And let me get the light up. Open. So what is this? This is electromotive force. Now, electromotive force one best way, what can provide electromotive force? A battery. A battery can provide electromotive force, provides that potential difference, that something to push electrons through the wires to cause the current. So you can have a battery, and a battery can provide electromotive force, but another way to do it is you can induce it, much as like what we talked about charging by induction. You're doing something that causes, either in the case of charging by induction, you're causing charges to shift. Here, we're messing with the magnetic fields. Magnetic flux is phi sub b, capital phi. Phi sub b, magnetic flux. Phi sub b is the product of two quantities. Magnetic field and area. Now, what we've talked about before is, why is the magnetic field called B? Well, that's because the guy who basically classified all of electrodynamics got around to naming the magnetic field second, and he was just being alphabetical. Since magnetic field was the second quantity that he was dealing with, he just went A, B, C, D. B was magnetic field. There you go. That was the reason. This d phi b dt and magnetic flux, I've tried to make the analogy of volume of wind passing through a window. That, truth be told, in the physics 213 way of doing things, this is all we really need. But truth be told, magnetic flux is in reality BA cosine theta. Now, that theta is the angle between direction of B field and normal line of surface. So in a situation where we've got our window or our surface here, the normal line, just as we have had normal force, the normal line is perpendicular to the surface. So we can do an n, you can write n vector or n hat, a lot of times people use. And in the case of a B field being like either out of the window or into the window, the theta here is either 0 or 180, and cosine of theta in this case is 1. And so this is why flux B, well, 1 or negative 1, but all I really care about is the magnitude. And so BA, well, at this moment I only care about the magnitude. And the magnetic flux is BA. In this case, if the wind or the magnetic field is going parallel to the surface of the window or perpendicular to the normal, the theta in this case is plus or minus 90 degrees, and the cosine of theta, cosine of 90, is 0. So magnetic flux is equal to 0. So in 214, the B field will always be perpendicular to the surface. In 212, the B field can be all sorts of angles. So in terms of, because we're 213, 214, we're mathematically a little bit more diluted than the high proof or high test 211, 212s. So all of the B fields that you're dealing with are going to be perpendicular or perpendicular to the surface or parallel with the normal.
Dr.
Yes.
In the equation, d phi over dt,
Yeah.
by d, do you just mean change it?
The change, yes.
So it's the same like delta.
Yeah, and in much like velocity is dx dt,
Right.
like acceleration is dv dt. So when I write this, to those of you who have taken Math 262, which is the Cal 1, okay. I mean, so small number of students in this room have taken Cal 1, Cal 2. When you see something like this, really you need to make the association with velocity change in position with respect to time. And that's how you should read it. For those who have taken 262 and onward, it really just means the first derivative of that quantity, which, since I've got my hands tied behind my back with respect to calculus, that you're just going to have to, you treat it more like you treat d dt as like a symbol of change with respect to time, and that's how I would equate it. Now, this equation specifically, this one right here, is called Faraday's law. Faraday's law, by definition, is that the electromotive force is the negative of the change in flux with a magnetic flux with respect to time. What I'm going to do is I'm going to rip Faraday's law apart a little bit, explore it. What I'm really interested in is when I get done with it, we all understand my particular philosophy on physics, that I'm more interested in the equations governing the magnitude of quantities and then your logic determining the positive and negative signs. I want you to rationalize this rather than the equations or the calculator trying to tell you what to do. In a little bit of backstory, we're all familiar with the X and Y axes, and we all understand that right is positive and that left is negative, and that Y is positive, and then down is, or down the page is negative Y. And there have been a few people who have been asking about, well, why is the Z, the third dimension, why is out of the page positive and into the page negative? I mean, and truth be told, it's the way that we're handling it. As long as you know that into the page is opposite of out of the page, that's good enough for us. But there is a reason why. And it's because we live under the oppression of the right-handers, is we live in a right-handed coordinate system. And one of the things that is fundamental for a right-handed coordinate system is that x cross y is equal to z. So x to the right, y up the page, thumb points out. So x cross y will give you z. Z is outward. Positive x, positive y gives you positive z. So positive z is the outward symbol, negative z is the inward symbol. And one of the things, and it's actually attendance has improved since about 10 minutes before class. One of the things I'm headhunting for, I do it in 213. I get more of this in 213 than 214 because the 214s, most of you are my students. So really what I'm looking for are a couple of Marshall students who've never attended class, is when they see this right-hand rule game, which will be the appetizer problem on the test, I'm looking for the students who basically raise their hand and I go over and then they go, what is this? I don't understand what this is. And it happens about once a year. And really what's really interesting is that the other students look over because I warned them like I'm telling you right now, is when that person stands up and talks to me and says, I don't know what to do with this, they've just announced to the class that they don't go to class. That they not only don't go to class, but they don't do their homework. So it's just a little warning that going to class is a good thing. The solution to missing class is not to miss more class. I know that sounds so counterintuitive, but just a little bit of a service message. So we understand that up is positive and down is negative, and we understand because we all remember when another thing in philosophy that I do is I look like an idiot in front of the class. I kind of burn a memory into your brain. And what do we know about that direction? That's to the right, that's positive. So if I'm moving to the right, my velocity is to the right. If I'm moving to the left, my velocity is to the left. If I am moving to the right and speeding up, my velocity is to the right and my acceleration is where? To the right. If you're speeding up, velocity and acceleration are in the same direction. If I'm running this way but slowing down, my velocity is this way and my acceleration is where? That way. When you're slowing down, it's opposite. Speeding up, velocity and acceleration are the same. Slowing down, they're opposite. This is a very important aspect that we need to remember. Now, for the test, we know that the appetizer is the right-hand rule game. Kirchhoff's laws will be one of the big problems. Really, all that it comes down to is the I of the mid resistor. The next one is B field addition.
Is that capital I? Is it always just
This
well, no, wouldn't it be? Wouldn't we get this now more problems?
current is whatever letter I assign it. In the way that I handle currents, it's lowercase I. The way that the lab instructors do it is they use capital I and then they specify a direction. It's lowercase I. It could be either. It's whatever. The number 2 problem is the B field at a particular point, B field addition, or it could be a wild card. The wild card force on a wire, particle spectrometer, velocity selector, stuff that we'll go over Thursday and stuff that we've already covered. And then the third one is magnetic induction. Also, that's been, what has been posted on Blackboard is there are 2 files called tests. One is a test from last summer, I think, and then the other one it's called test T2 pack, and the T2 pack has 2 earlier tests. You can use the test from last summer for the multiple choice and the problems, the other tests for more problems, and given enough time on Friday, I mean, we could work some of those out. Given enough time this Thursday, we can work some of those out, whatever you guys want to do. So for problem number 3, what I'm really interested is the magnitude of this electromotive force, which is d phi b dt. Because we are limited Some would say that because we're protected and we're merely only Physics 214 students, the magnetic field has to be perpendicular, and if we do this, the magnetic flux is B field times area. Oh, I'm sorry, not DDA, DDT. When you've got two quantities, B field and area, and they could be functions of time, could be, what you have to do is you have to do something called the chain rule, which basically is you take the derivative of the first multiplied by the second times the first times the derivative of the second. You can ignore exactly. Your confusion is unnecessary because I'm going to tell you what you need to do. The chain rule is for like physics, or I'm sorry, the 211, 212s. It's for Cal 1 students, and it should be read like d dB dt plus b dA dt. Now that's basically what the chain rule says. Also, we're limited by the fact that I would love to be cruel, but for purposes of keeping people sane, you only will change A or B with respect to time. That in the problem that shows up on the test, the B field's going to change or the area is going to change. So if the B field changes but the area doesn't, if the B field changes and the area doesn't, what is dA dt? It's 0. So changing B field only, that magnitude of electromotive force is AdB dt. And if it is a changing area only, the electromotive force will be B dA dt. So it's got to be one or the other. Now this will be given, magnetic flux is equal to BA will be given. But in terms of you understanding how it goes from there to here's, you need to remember how that goes. There are two main types of problems, both of which are on problem set 5.
You need to look at
The projector is overheating. Make sure nothing is blocking the air vent. Clean or replace the air vent. Only thing I can do is open up a window. There we go. Do me a favor, over on that window, open one of those windows up. Just lift the locks up so we can get a crosswind. All right, it's picky. See, I fixed it. Oop. There we go. Now, there are going to be two types of problems in problem set 5. The changing of the B field only, you get a loop, you get, you can have a B field. The B field would be into or out of the page. And then the changing of the B field can be into or out of the page as well. And then you get something like a radius of the circle. We're only going to be dealing with circles. You've got to, of course, know the basics: circumference of a circle, area of a circle. Things like a third grader geometry student would know, I expect you to know as well. And then this wire has a particular resistance. And so a lot of the questions that are asked is magnitude of current and clockwise or counterclockwise. That to answer a problem like this, you're going to be given all sorts of information, but the primary thing that we're focused on at the moment is this magnetic induction causes a current. Is the direction of the current clockwise or counterclockwise? What's the magnitude of the current? What's the magnitude of the electromotive force? Stuff like that. Right now I'm just describing the problems. For a changing area, it looks a little bit more complex. Oh, I know. Okay, hold on. In this particular case, nothing moves. In this particular case, and that's when the garbage truck shows up. The bar right here is the only thing that can move in this particular problem. So this is a moving bar. And the bar can move either left or right. It's sitting, the bar and everything to the right, is sitting in a magnetic field that can, of course, be up or down. Today, we're only going to work with one or two of the permutations of each. There are, in fact, 4 permutations for each of the problems. I'm going to try to get a hold of, or I need to find, basically one afternoon in front of a class in the tutoring room in the physics department. I went through every single permutation and drew it out, and then I took photos of it so that, future students could take a look at it. In this particular case, the questions that are typically asked are, what is I? Is it clockwise? Is it counterclockwise? And the force on the bar. And direction of force on a bar. So left or right. So these are the 2 types of problems. Now granted, we're just doing a review over what they could be. But as a, speaking as your as you're going into tutor mode for just a moment, one of these problems will be on the test, one will be on the final. So for the test, you kind of go, well, I got to be ready for both. The moment you see what's on the test, you immediately know what's going to be on the final. Because there's no sense in me asking the same question twice. Yeah, it'll either be this one or that one. Now, there are a whole bunch of variables, and I can change it up so that instead of asking for current, I could give you current. But we'll go on. Yes? How do we do that? Excellent question. Which is the beginning of what we're going to talk about now. I'm not going to talk about that one just yet, but this one let's talk about. When you've got a B field, and that B field is changing, and it's passing through a region. Let's say for the moment that the magnetic field is out of the page. And let's say that it is increasing. So this B field, let's say the magnitude is 0.1 Tesla out of the page at time equals 0. And if it's going 1 second, 0.2 Tesla, 2 seconds, 0.3 Tesla, 4 seconds, etc. Its dB/dt is 0.1 Tesla per second. That the change in the magnetic field, magnitude-wise, is 0.1 Tesla per second, and because the B field is going out of the page and getting stronger out of the page, that dB/dt is also outward.
Dr. Eschenberg?
Yes.
Just by virtue of the fact that we know that the B field is coming out of the page, does that indicate to us that the B field is increasing?
No.
Okay.
If I said that the B field, if I gave you data points that said B field was 1 Tesla, 0.9 Tesla, 0.8 Tesla, 0.7, then you know that dB, let's say B was up, and then it was 1 Tesla up, 0.9 up, 0.8 up, you would know that the dB/dt was 0.1 Tesla per second down.
Okay.
But it's still going out of the page.
B field would be going out of the page, but dB/dt would be going in. So this is our sheet of paper. And I say that the B field is at you, so it's a circled up. And it goes 1, 2, 3. Is dB/dt out of the page or into the page? It's out. If I said it's into the page at 2 Tesla, and dB/dt was going out, at a later time, would it be 3 Tesla into the page, or would it be later 1 Tesla into the page? It would be 1. Because if it's 2 into the page and dB/dt is out, it will never be 3. It will eventually become 1. And then with enough time, then it would shift outward. So this is where you guys need to think about the analogy that I made earlier with velocity and acceleration. That it is possible to have velocity in the opposite direction of acceleration. And
So the vectors that are pointing in and out of the page are like imaginary roadways that, like in first semester, we had a race car.
yeah, exactly. I would, yes, you could use that as an analogy, yeah. So in this particular case, the B field is out, the dB/dt is out. If the B is out, the magnetic flux is out. So you can think of what I'm building towards is technically, well, not sure if I want to introduce the idea of magnetic flux as a vector, but think of the B field direction out of the page times the area is going to give you a value. And since I consider out positive, the flux will be positive, and you can associate that with out.
Like you said earlier, the wind's going out of
The wind, yes, exactly. The dB/dt is out. So the A dB/dt, or the change in flux with respect to time, is also going out. If the change in B field was into the page, the change in magnetic flux with respect to time would be into the page as well. Yeah. B is in the same direction as the magnetic flux dB dt is in the same direction as d phi b dt. But it is not required that the B field will always point in the direction as the magnetic flux. The dB dt will always point in the same direction as the change in magnetic flux. But it is not required that the magnetic flux and the change in magnetic flux go in the same direction. So those two vectors can be both out, both in, opposite. It doesn't matter. It all depends on the external changes that are going on. Now we have to introduce an idea that is called Lenz's law. And Lenz's is actually spelled with a Z. Nature, like students, hates change. Doesn't like it. Nature will do what it can for as long as it can to oppose the external change that is trying to go on. Effectively, what's going on is nature loves something that's constant, something unchanging. And if suddenly we all blow wind into the page, nature hates that. And it will try to briefly oppose it. If, for those of you who have ever dabbled in electronics, you like coils, inductors, things will oppose certain things that go on. If you blow into a page, nature will try to do something to blow out of the page to make sure that the net wind going through the page is zero. It's just the nature of the world, the universe. If you blow into the page, it will try to blow out. If you try to pull air out of the page, it will blow in. It will oppose the action. In Faraday's law, Lenz's law is that negative sign. That negative sign comes from the idea that nature doesn't like what's going on, so it will oppose it to keep the balance. Now, in reality, eventually it just gives up and slows down. But When a change in magnetic flux is externally applied, an electromotive force is induced to oppose this change. This is where the current is created, or this is how the current is created. To do this, well, because of this EMF, the EMF creates a current which then creates its own B field and magnetic flux. So when a change in magnetic flux is externally applied, this causes an electromotive force to be created. This electromotive force causes a current to be created, which causes its own magnetic field to be created. This magnetic field and they're both really all parallel. I've labeled in green the induced B field and d phi b dt is always opposite of that. Now, to those of you who, one thing I don't like about the overhead projector is it sucks out the color. On the video, you can see it. Those two are the same quantity, which is this. This is the same as these. These are always opposite. These are always opposite. The external change in magnetic flux with respect to time is always opposite of the induced flux with respect to time. Always, always. Now, because I have said that it is not required that magnetic flux and the change in magnetic flux both point in the same direction, they can be in the same direction as the normal external B field. They can be opposite. What d phi b dt and that induced B field only care about is the d phi b dt. The induced magnetic flux, the induced magnetic field, only cares about the change in flux with respect to time. Does it care about the external B field? No. It only cares about the change in the.
So Dr. Ashenberg, this is basically a wire loop that you put
In a changing magnetic field.
magnet next to it or something.
Yeah.
And it's increasing.
Mhm.
And then you get I guess a charge or whatever.
It will-
passes
it will-
around the
yes.
wire. It creates new.
Mhm. What kind of current would create something like this? A current going, a magnetic field into the page. A clockwise current. A clockwise current would create a magnetic field going into the page. So the induced current in this particular case is running clockwise.
I was just a little confused over.
Yeah, it's a lot like, it's the equivalent of this is a wire loop, this is a magnet. As the magnet gets closer to the loop, what happens? The magnetic field increases because you're getting closer to the bar magnet. So what happens is the B field is increasing into the page. The B field is into the page. Because it's increasing, the dB dt is into the page, which means that the change in flux is also into the page. So the induced flux must oppose this. And what's the only way to get a magnetic flux out of the page? Is if this wire has a counterclockwise current. And so that's how you would get it. Now this is another permutation. And the permutation, actually what really this is this problem looked at from the opposite side.
So your current of the wire is just what you're induced and it's not what you don't do it based upon all the other.
Well, the only thing that this cares about is that quantity right there. It does not care about the B field itself. It cares about the change in flux with respect to time. And now we can get all mathy. The electromotive force, magnitude, now really what I'm doing with this is I'm just writing magnitudes, is d phi b dt. Because it's a changing magnetic field, the electromotive force is area dB dt, and current, which is electromotive force divided by resistance, is equal to A over R dB dt. And in this, so the current is the area divided by the resistance of the coil times the change in magnetic field with respect to time. So that's how you form the relationship between the magnetic field, the change in magnetic field, the current, the area, the resistance.
Why is it electromotive force over resistance?
Why is electromotive force over resistance current? Ohm's law. So really, what I did is I took compared to the moving bar, the loop in the external changing magnetic field, the bar one is a little bit more complex. So what I did is I used the simpler problem to explain Lenz's law. Because Lenz's law is kind of a weird, loopy conceptual conceptual idea. Whew. All right, next. Now also what's going to go on is I'll get that study sheet so you can go through all the permutations itself. In my estimation, magnetic induction is the loopiest of all the problems you're going to deal with in 214 in terms of three-dimensionally conceptualizing what's going on. The second example, we have a region of magnetic field. This magnetic field is constant, and let's just say it's into the page. There is a wire with a resistor. Now these wires go on infinitely, but they never touch again. Here, that's a bar, and I'll make it moving to the left with a particular velocity. So the first question that I have to ask is, what is the current going through the bar? Is it clockwise? Is it counterclockwise? And that's the problem. There's a great demonstration of this in, like, if you go to the Exploratorium in San Francisco has it. It has, like, basically what you have is like a big loop in a slot, and in the slot are these magnetic, basically just these big magnets. And what you do is you push the hoop into the slot, and what you feel is a force on the loop, which is this is effectively a simplistic version of that loop problem. So think of this as a bar moving into the slot or whatever. What's my area? Well, the area is that. The area of the magnetic field in the circuit is this region right there. An area is, we'll call that X, and we'll call that L, the length of the bar. A is X times L. So I've got a moving bar, the bar is of a particular length, it's a certain distance within the magnetic field, and I go, well, what's the electromotive force? What's that magnitude? Well, you go, well, that's d phi b dt. But the next thing you know is that magnetic flux is equal to BA. So this becomes d dt of BA. B doesn't change. So this becomes BdA dt. And what is A? D dt of XL. Now what we're doing here is, to those of you who have taken Cal 260 or Math 262, we're doing the chain rule twice. The first time we did the chain rule, we went from there to there, but we got rid of A dB dt because magnetic field doesn't change. This is XL. The area is the depth X times the length L. Does length change? No, the bar length doesn't change. So what I can do is I would chain rule it again to get this. And what do I know about dx dt? What's dx dt commonly referred to? Velocity. The dx dt is velocity. So this just becomes BLV. The magnitude of the electromotive force is just the magnetic field times the length times velocity. It is X independent. Pendant, whatever. It doesn't matter what that depth is. What does matter is the change in X, the velocity. That does matter. A lot of times when assigning a problem like this, I'll give you X. Just say X is 5 meters. And then I'll sit there and watch you try to squeeze 5 meters into the problem. Because you don't need it. Not at all. Now, if I said, well, what's the flux? Well, the magnetic flux in this case, obviously, is B times A, which is B times L times X. So if you had to get the magnetic flux, I mean, then you would need the depth. But in terms of the electromotive force, no, you don't. Then you use Ohm's law to get the current. So the current induced is BLV divided by R. When assigning a problem like this on the test, I want to see the derivation. And I may even I'm trying to do something that will ensure that you have to do it. So that gives you the current. Now, the important thing that a lot of people ask is, how does this relate to the problem set? And when you look at this, it's the two types of problems, but in some cases, I give you different sets of variables. Are we getting the final visit from the truck? No, it's just the bus. So what I've done for you is there's one last bit, which will take about 8 minutes. But I've effectively done the problem set for you. All you have to do is just repeat, lather, rinse, repeat the derivations that I've gone over right now, apply the conditions that I give you, and then you've got this stuff. Yes?
Can that wire configuration right at the beginning, can that be like different, or will it always look similar to that?
It'll look similar to that. The lines will always be parallel. The bar will always move from left to right or right to left.
The same thing with where the B field changes to?
Mm-hmm. Yeah, but you won't get a changing B field on this with a moving bar. That would be delicious, but not for your class. Yes? Let me get to that. That's the extra bit. So, Adrian, this moving bar has a current running through it. Is the bar in a magnetic field? No pressure. You say no? Oh, you said yes. Well, of course, because it's sitting right there in the middle of the red region. So, of course, it's in a magnetic field. And what happens, Sabrina, when you have a current wire, a wire carrying current in a magnetic field? Isn't there a lab coming up? I think there is a lab coming up where you have a wire carrying a current in a magnetic field. What should it experience? It experiences a force. That force on a wire is ILB. Oh, that makes perfect sense now. So that force is I, or BLV over R times LB, or VL squared B squared over R. So the force on this bar, by the fact that it is carrying a current through it that we've set up, will experience a force. Now, one of the things that I'm going to do is, once everybody gets the notes for this, I'll talk about, I'm going to blow this up, put it big on the screen so that we can talk through this. Because we haven't figured out the main questions, some of the main questions. We figured out what I is magnitude-wise. We figured out what F is magnitude-wise. But we have not figured out the current direction, nor have we not figured out, is that a double negative? I don't know, I don't care. But we haven't figured out the direction of the force. So I'm going to blow this up. So last chance. 5, 4, 3, 2, 1. Okay, here we go.
Number 1 and 3 are basically the same problem.
Excuse me?
Number 1 and 3 on the problem set are like the same problem, but different.
Yeah, different numbers. And really, the benefit that I'm giving you is if I do it with letters only, all you got to do is just throw in numbers. It's not that big of a deal. All right.
You need to show the full derivation. For
Yes.
single problem.
Yes. Because I'm trying to figure out ways that'll require you to do that. I think it's like bullet 5 or 4. Miracles do not occur on this test. You must show all
Yeah,
steps.
we need to show
It's a pretty easy derivation. Yeah.
chain rule derivation.
I wouldn't go full chain rule. I would just say, just kind of explain it as you're going. Well, don't worry. Me and the graders will be on the same page when it comes to what is an acceptable leap.
Like, could you skip from DDT via?
Let's focus on that on Friday.
Okay.
Good question. Don't forget. Because I only got 11 minutes. The B field is into the page in this particular case. Question. The magnetic flux, is it into or out of the page? Into. Magnetic flux and B field are always in the same direction. Next, the bar is going to the left. Is the area getting bigger or smaller? Smaller. The window is getting smaller. So tell me about the magnetic flux. Is it getting smaller or bigger? The window is getting smaller. The magnetic field remains the same. So the amount of wind that can get through, which is our analogy for magnetic flux, gets smaller. Which means that a smaller window and a smaller magnetic flux means that d phi b dt is out of the page or in any opposite direction. Analogy. If the bar is getting to the right, area increases, the amount of magnetic flux increases, and those two are of the same direction. If the bar is going to the left, the area is getting smaller, the wind is decreasing. These are of opposite directions. So, and one of the things that I did on, I think I did on the notes, is I wrote that analogy down.
So if B was pointing to the right, it would be right to the page? Or no?
Let's deal with the permutations later. I'd be happy to talk about that.
So why is 5B out of the page?
5B is
Or
this,
to the page.
phi B is into the page because phi B is always in the same direction as B. The wind is going into the page, so the flux has to go into the page. The area is getting smaller, so the change in flux has to be in the opposite direction. Lenz's law says, I hate change. The change is out of the page, so I must induce a change into the page. So the induced is into the page. Induced flux is always opposite of external change in flux.
So the direction of the current of the wire would be based upon the induced.
Exactly. The induced magnetic flux is into the page. So what is the only direction of current that could produce magnetic field and magnetic flux into the page? A clockwise current. Now, this clockwise current, with respect to the bar itself, is the current running from top to bottom in the bar or from bottom to top? Top to bottom. So if the current, thank you Sabrina for bringing attention upon yourself. The current is going from top to bottom, so in which direction is the magnetic force?
Top. The bottom to top? Or
So the current is going from top to bottom. In which direction is the magnetic force on the bar?
top? Bottom to top.
What is the right-hand rule game that we play with force on a wire in a magnetic field? I cross B, which has been mentioned before. So I is from top to bottom. B field is what? Into the page. Which means that the magnetic force is to the right. So the magnetic force is going to the right. So the magnetic force is going to the right. In the problem sets, you may see external force. That's the force that you're pushing on the bar. In order to get the velocity to the left, the magnetic force is going to be to the right, which means I'm only going to draw the bar. Oh.
So when you do I cross B, you're doing the current running through the bar?
Yes. So the I is down, the B field is in. That means the force on the bar is to the right. Yes. To keep V constant, an external force must be applied. And FEXT is always opposite of magnetic force because What do you know about velocity being constant? Acceleration is 0. Oh, sorry. So in order to make it 0, FB is to the right, so external force must be to the left. So the external force is of the same magnitude so it's that. In order to maintain a constant velocity, external force and magnetic force always have to be opposite of each other. If the force on the bar is to the left, external force is to the right. And vice versa, like we have here. All right, I'm going to post some notes. This lecture will be online in about an hour, and that is it.